In chapter 28, we look at an electron in a box, a particle in a box system. When we look at a particle in a box, we can see that we only have certain possible energy states that are available to the electron. But in fact, an electron in an atom is like a particle in a box. The electron is constrained. It has to exist within the vicinity of the atom. And so because of that, it can only have certain possible energies. And so we're only going to have certain possible energy states available to electrons in atoms. And so we can only have certain possible energies of light which are emitted. Now think about this. Let's look at a quantum system. Here's a quantum system with different quantum states, different energy levels in which an electron can exist. And an electron can move from one state to another. It can jump from one level to another. But when it does that, because energy is conserved, it has to get rid of that energy, and it does that by emitting a photon. So an electron jumps from one energy level to another. When it drops from a higher level to a lower level, it gives off a photon. And the energy of the photon is equal to the difference in the energies of the two states. So here's a question. Look at this system of quantum energy levels. If an electron can make a transition between different states in this system, what is the lowest energy photon that could be emitted? We'll give you some choices. Well, let's take a look at the energy levels. If an electron is in state n equals 2 and drops to state n equals 1, it drops by an energy of 1 electron volt. It drops from 2 electron volts to 1 electron volt. The difference is 1 electron volt. And so the energy of the photon that's emitted is 1 electron volt. That's the smallest possible jump that we can have. And so therefore, it's the lowest possible energy photon that could be emitted in this system. Now let's look at a second quantum system. In this case, we've got a bunch of different energy states which are available to an electron, and it can move up and down to different energy levels. So it's going to think about an electron dropping from a higher energy level into a lower energy level. Which transition will correspond to a photon with the shortest wavelength? Think about it. We'll give you some choices. Well, we saw early in chapter 28 a formula for photon energy. And the energy of a photon corresponds to the frequency. It's proportional to the frequency. So if I have a high photon energy, I have a high frequency. But given what we know about waves, high frequency means a short wavelength. So the shortest wavelength is the highest frequency, which is the highest photon energy. And so as a consequence, this is a drop from energy state n equals 4 to energy state n equals 1. That's an energy difference of 5 electron volts. That's the highest energy, and so therefore it's the highest frequency, and so therefore it's the shortest possible wavelength. And now we have the studio illuminated by the light from a single light bulb. Now this is an incandescent bulb. There's a filament in the center that's a hot wire, and because it's hot, it gives off light. But it's giving off light because of the vibrations at an atomic level inside here. And the vibrations can be at any frequency. And so the light that it gives off is a mix of all the different frequencies, and therefore all the different colors of light. If we put a diffraction grating in front of the lens of the camera, you can see a complete rainbow. We have a total rainbow. We get all the colors of the spectrum. But it's a very, very different thing if I look at the light that's emitted by atomic transitions of atoms. And so I'm going to bring in a series of gas tubes, and I'm going to start by electrically exciting this one right here in the center. And I'm going to turn the light off. Now we're going to electrically excite a sample of gas. And when we do that, you can see the rainbow that I get is not a complete rainbow. There's only certain energy states, and so only certain possible transitions, and so this is a line spectrum. It consists of certain wavelengths, but not all possible wavelengths. And this is the spectrum of helium gas. But different gases have different possible electronic states, different possible transitions, and very different appearance. This is helium, and this is nitrogen, and this is neon. Different energy states, different transitions, and so therefore very, very different line spectra. different atoms have very different energy level structures, so different possible transitions, and so very different spectra. And that's a big part of the story that we'll talk about in chapter 29.